this formulation, this form of the Fourier transform of the derectified signal is very useful because we can now design a filter which will reconstruct the original signal. Indeed, what we gotta do? We already have it here. So this is the spectrum of the original signal, of the derectified signal. So I simply take a box with amplitude Ts, because I need to remove all these spectra, all these copies that I don't need it. I only want the main copy at 0, but this is scaled with 1 over Ts, so I multiply by Ts. So the filter that we want is h of j omega, which we can notice with h of omega, equal to Ts, which multiply u of omega plus omega sub s divided by 2 minus u omega minus omega sub s divided by 2. That's what we want. And that's what, and it will do the job. So we can recover the original signal by simply the original spectrum by multiplying this spectrum with this filter. And let's see what happened in physical time, in the time domain. So we got this xs of omega, which is given by the infinite sum of 1 over Ts of capital X of omega minus omega sub s of k. And we saw that the filter that we need is Ts, the box function, omega plus omega sub s divided by 2 minus u omega minus omega sub s divided by 2. Because we saw that we have all these multiple copies, and we saw that this is basically 1 over Ts x of omega, for example. So the spectrum that the filter that we design is basically a box filter, which is this. And we want to extract this quantity, okay? And so if we do xs of omega times h of omega, we're gonna get back the original signal, the original spectrum x of omega, as long as omega sub b is less than omega s divided by 2. Okay, the Nyquist Criterion. What happened in the time domain? In the time domain, this implies that if we convolve the original signal with h of t, we're gonna get back x of t. The question is now, let's understand what is the impulse response. The impulse response, impulse response is basically the inverse Fourier transform of h of omega. So h of t is 1 over 2 pi integral between minus infinity and infinity of h of omega e to the plus j omega t in the omega. Is right? So let's do this calculation and see what is the form of this spectrum of the impulse response. This is equal 1 over 2 pi. And now this signal, the impulse response, is only localized between minus s divided by 2 and omega s divided by 2. So this is equal to integral between minus omega sub s divided by 2 and omega sub s divided by 2 of what? Of amplitude ts times e to the j omega t in the omega. And let's do now the calculations. This is pretty straightforward because it's going to be equal to, I take this and bring it outside, and I will have ts over 2 pi of this integral, but this integral it's easy because it's equal to e to the j omega t divided by jt, computed between minus omega sub s divided by 2 and omega sub s divided by 2. And this is equal to what? Is equal to t sub s divided by 2 pi e to the j omega sub s divided by 2 times t minus e to the minus j omega sub s divided by 2 divided by t divided jt. But now I can apply the Euler formula because I remind you that sine of x is equal to e to the jx minus e to the minus jx divided by 2j. And as you can see, I can rewrite, I can take this coefficient altogether and write it as ts of e to the j omega s divided by 2t minus e to the minus j omega s divided by t divided 2j. This is ts over pi, and then here I have t. So all of this is basically the sign of this quantity. So this is equal to ts over pi t times the sine of omega s divided by 2 times t. But now we can, so this is the impulse response. We can rewrite this quantity here as h of t equal, let me remind you that the cyclic frequency, sampling frequency is this. So we have sine of 2 pi over ts t divided by 2 divided, I can write this as pi ts divided by ts. 2 and 2 simplify, so you will see that I get the nice formula pi t over ts and sine of pi t over ts. Of course, this filter is non-causal. But that's okay, and that's what we got. But let's see how we use these results. So we found that the original spectrum can be computed by multiplying the spectrum of the derectified signal by the filter response, the frequency response of the filter. And in physical time, so h of omega is basically it was a box signal. It was a box filter. And in physical time, we get what? That x of t is going to be equal to the convolution between the derectified signal convolved with the impulse response. So this is the continuous signal. This is the directified signal. and this is the impulse response. And we see that we have seen that this is true as long as we satisfy the Nyquist criterion. Okay? But let me remind you that xs of t was what? Was the original signal multiplied by the Dirac train. And this one was equal to the sum from n equal minus infinity to infinity of x of nts delta of t minus nts. But now we know what is h of t, because we know that h of t is equal to sine of pi t over ts divided pi t over ts. And then, if we carry out this convolution, we can write x of t equal to what? To the convolution of this sum with h, is right? So we have the sum over n of xn t sub s delta t minus nts convolved with h of t. But this is going to be equal to the sum over n of x and ts. This convolution of shifted delta with h is going to give me the h, but shifted by the same amount. And that's where we get the beautiful formulation of the Shannon Theorem. The Shannon Theorem is telling me that as long as the Nyquist frequency is satisfied, I can recover the original signal exactly by doing these linear combinations of the sampled values times the impulse response, which is given by this form. And this is an exact result as long as we don't have no aliasing. Okay, so then the Nyquist frequency has to be satisfied, and that's a beautiful result. So let me summarize the main steps that allow us to arrive to these results. So we started with a continuous signal. We multiply by a Dirac train, and we get the Diractified signal. This it is passed through a filter h of omega that we know what it is, and we can recover x of t as long as the Nyquist frequency, the Nyquist criterion is satisfied, no aliasing. And what were the main steps here? So we had what? We had in the frequency domain we have x of omega. Then we show that the Fourier spectrum of the Diractified signal Diractified signal can be expressed as the sum from k equal minus infinity to infinity of infinite copies of infinite shifted a sum of infinite copies of the original spectrum, but shifted by ts, and here we have 1 over ts. Okay, and the filter was very spatial, so was given by a box filter, given by omega plus omega sub s divided by 2 minus u of omega minus omega sub s divided by 2. And in the frequency domain, so we got the following, in the frequency domain, we got the following picture. Omega, omega, 0, 0, omega sub s, omega s, minus omega s, minus omega s. Here we have the middle values. Omega sub s divided by 2, minus omega sub s divided by 2, omega sub s divided by 2, minus omega s divided by 2. If the original spectrum it is bounded and satisfy the Nyquist criterion, so omega b is less than this quantity, then what happened? This is the x of omega. Then we have that the spectrum of xs of omega is given by multiple copies of the original spectrum. So basically 1 over ts x of omega, this is 1 over ts x of omega minus omega sub s, and so on. And then the filter that we want is simply given by this. With quantity ts, and in the time domain, the filter is given by the following functions. This is h of t, the sinc function. And that's the main results, okay? So you can see that the filter is equal to 1 at t equals 0, and then he has 0 values at all at ts, 2ts, 3ts. So because he just have to sample the values, has to extract the value at t equals 0. Now, what happens if this condition is not satisfied? And then we will have aliasing, and we cannot recover the original signal because we get spurious frequencies that are aliased onto the spectrum. Let's see how this. Let's see a case in which omega b is greater than omega s divided by 2, we have aliasing. That would be the following case, something like the following. So omega, this is 0, 0. Now here we have omega s, 2 omega s, omega s, 2 omega s. Then we have minus omega s, minus 2 omega sub s. And of course here there will be the middle values, minus omega s divided by 2 plus omega sub s divided by 2. What's going to happen now that the spectrum, we are undersampling the signal. So for example, now the spectrum is going to be half away, be something like this. Okay, this is the original x of omega. So what's going to happen now that when I start to do the sampling, when the spectrum of the rectified signal it will be given by what? So I still have the original ones. This is 0. This is omega. So this is minus omega s. So I have this. Okay. And but then I'm gonna have another copy that is gonna be shifted at omega s, and this other copy is gonna be basically given by the following. Then I have another copy here, which is gonna be given by this. So you see that now there is an overlapping region, and at this point the spectrum double it, the amplitude. So you see that that's what we get, and so on, okay? And of course, now if you apply the filter that we defined before, you see that this quantity here basically is alias in this quantity here, and so this quantity here basically is alias back on this, and so our signal basically it is corrupt. So we get this alias frequencies that they're gonna corrupt the reconstruction, and so we cannot recover the original signal because we have aliasing. Okay, and that's conclude the lecture. Thank you.